Okay. So the recording is running, right?
Yes, the
Nice.
recording is running. Yeah.
Nice. Okay. So welcome. Today we're going to talk about DevOps+, so turning green IT ambition into daily engineering actions. It's one of my daily focus and what I love to do. Before I tell something a bit about myself, and this is also about myself, this is where I grew up. So my dad was a night guard, and we lived literally on a factory. So I've seen as a child, although I saw it at that time differently, what negative impact can do, especially with the surrounding. If you see the dust clouds on the right top, that was also coming down. Not really good for our health. So yeah, fun fact. Well, fun is that now, since the zeros, it's a recycling plant. So it's completely changed from that perspective. The only thing is, this is not anymore in the Netherlands. It moved to China. So what I always say, because if you don't see it, doesn't mean it is not there. So like I said, I'm very focused with this topic. So this was me at Green IO in Paris at end of 2024. I'm a Green Software Champion, and I'm also very involved in the academia world, trying to help assistant professors to have certain research topics that we need as applied science eventually in our line of field. So yeah, why DevOps++ exists? Because it's something that I created together with my team, especially in the last year. And the main reason is modern digital systems generate waste through idling. So there's a lot of waiting everywhere going on. Most of the time, if something doesn't work, we just scale up. So eventually we create oversized resources, or we just create something default and never look back at it. And yeah, there's also a lot of inefficient software, sadly enough. We always think that we build the coolest and most efficient things, but if you really sometimes go look into it, there are, especially at scale, a lot of inefficiencies going on. So DevOps+ addresses the core problem, and it has to do with this. I do more, how do you say? I like to do this more, go into nature and observe everything out there. Especially also because I worked for 2 years for Nature Data Bank, so I know where the observations you do, if you send them to a certain organization, where they end up. But it's more focused on how can developers and DevOps teams spot digital waste in practice. And where it all started was last year at Christmas. It's always a dangerous time for me, because at Christmas I'm not doing a lot of stuff. That means that I have a lot of ideas that I want to find out how those certain things work out and that kind of stuff. Especially that I'm focused mainly on this topic. So one of the things that I already earlier in 2024 figured out was that to have a better idea how software consumes energy, you need to know kind of how the software utilizes certain resources like the CPU. And I started first with some, measurement tooling. I will send links later, so don't worry if you don't understand what this measurement tool is. But most measurement tools, what's happening is that they often measure per second or per hour or per day, so very high over. While in software, if you have an API and that API only takes a few seconds, you want to know it in milliseconds. So the first thing that I need to kind of fix is that. So this is an example. You don't need to know the code for what's happening here, but this is in general what we often do in APIs. We get some data somewhere, and that is this peak, and then you do some sorting, and then you filter some data, and then maybe you do some group buying, and then you do some computations. And in this case, it takes 2 seconds. So for the people who don't know, so the Green Software Foundation is an organization where organizations like Microsoft, Accenture, GitHub, a lot of big or larger organizations are behind it. And they eventually took research from Google, where they said, like, if you're utilizing the CPU only at 0%, a lot of people expect them to not use a lot of power. So in this case, 100 watts, but you actually use a lot of power. So the most efficient range for your CPU to utilize, and we often talk then about the cores of the CPU, is between 70 and 80%. This is in the performance world, that is the case, but especially also in the sustainable and the green space, this is the case. And then this is also the reason why idling takes so much amount of energy, because if it's not doing anything, it still has a CPU package. It is the base kind of the CPU that consumes that energy. So yeah, we built some tooling that especially focus on that 70, 80, 90%. Just know that there are kind of ways to create reports. I want to focus on this. So almost any software these days runs on Linux. And although you can have all these tools for calculating energy and emissions, one of the most simplest things you can do is reading the virtual file procstat. So it's something from the Linux kernel itself. You can use any programming language that can just say, read this file. So in this case, procstat. And it will give you, at that moment in time, all the time that certain cores have spent on the kernel time, on running something, so that's user time, or idling, actually doing nothing. So if you kind of read that file very quickly, and in most cases, there's a configuration that is a default a clock tick on 100. That means per 1,000 milliseconds, that every 10 milliseconds, that in this case, it tries to dump to this file. Often it is 20, 30 milliseconds. But it means that if you read it very quickly, almost every 10, 20 milliseconds, you can get measurements and you can put it in the memory. And then afterwards, so like you're running some code and you're doing this at the same time, you can see then the delta. So what I mean with it is if you measure every like 10, 20, 30 milliseconds, you can see how much user time at the meanwhile was going on. So in this case, in the simple example, there was 21 milliseconds user time going on, 0 system time, and a little bit of idle time, which means utilization of 70%. So by doing this, you can do very low time utilization estimates to see how kind of the software utilizes the cores and the CPU. So in this case, this is exactly what we did, and these are the data points that came out of it. In the ideal world, and this is what we did with workshops in the start of 2025, is that you want two things. You want to make it quicker, of course, because if you have an API that is quicker, you're using less power and less energy. The other thing is you want to use kind of all the cores that are available. So the question was always, can you have such an API like this that is very fluctuation going on? Can you make it stable? And the answer is yes. You have certain techniques for this. There's another thing that I'm not going really deep into in this presentation is the other reason why you want to make it stable is because the less fluctuation you have on the CPU, the less temperature changes you have, and over years, that means also less hardware wear and tear. Now, these days, that is more something for the hyperscalers that often don't care about it, sadly enough. But if you want to be more, how do you say, more aware of certain things, that could also be an important thing you could do. So, okay, so for me, because I was in the beginning, I was searching online about what can I do as a coder, what can I do as an architect. And most of the time what I read was that, yeah, just write beautiful quality software and it's going to be great. But sadly, it can happen that you write very efficient algorithms, very efficient code, but that you even use more energy. So I needed to understand better how CPUs work. So I had this eureka moment that was like, there are kind of three main things with a CPU. One is you queue up code that will be executed, that will be, the instruction will be executed. But the second thing is there will be moments of waiting going on. And the third thing is to utilize all the cores, you have to eventually use async and parallel coding. And all the three things, so when do you queue up code? How do you queue up code? We often do that with just coding and pressing F5 or running a certain program, and it will be queued up to the CPU and it's going to run. Waiting and the parallel have all impact on the energy use. So I will try to explain it. So most of the time, let's say in this case, you have a simple program running and you have only 2 cores. So you have 2 threads that you're using of that CPU. Most of the time, if you're the only person that is using the CPU in the cloud, you will never 100% know for sure. You're going to use then 2 cores. It will boost because it know like, hey, these cores, I have enough power. There's not going to be overheating. I can go to 5 gigahertz. If you wanted to use all the cores and it would boost all the cores, it would overheat. So the whole reason that there's fluctuation of frequencies going on is to kind of stabilize it and make sure that it's efficient, but it's not overheating the CPU. That also means that even with exactly the same code, you can have kind of how do you say it, different voltages. They're now here all equal, but they could be 1.1, 1.2. They can fluctuate as well, just like the frequencies. And that then also is the same for the wattage of the cores. So there is a link between how we code. So if we say we're gonna do a loop, or we're gonna do a fast instruction, or that kind of stuff, the way we queue up code to the CPU has influence on how it executes and how it then the cores behave. But with async coding, we also have a certain influence on it, and with waiting. So for instance, with waiting is the most simple. If you build a loop to wait on something and just every time checks like, is it other requests already done? No, then I'm going to loop again. You're using a full core. There are better techniques to do waiting or sleeping that is not using the full CPU core. So yeah, it's very down, as I said, a low level, but it's very good to have an understanding that this is, and that as a developer you have impact on it. Because most of the time we think, it's so the compiler is going to solve it, the runtime is going to solve it. We as developers have way more influences on this than we often think. So sustainability in digital systems is shaped by energy usage to some degree, because the sustainability is not only energy use, it is also how do you maintain something for a longer period of time. But let's focus on the energy first. So for people who this is new to, that's why I'm always putting this in the slides, is that if you look at like, you have electricitymaps.com, you have this for the whole world, and you can see per country how much emissions there are going on right now or in the past, how much CO2 per kilowatt hour. So what I always say, if you want to understand this, let's say if you have a microwave, and you put the microwave has a set an option to choose of 1,000, so 1,000 watts. If you run the microwave for 1 hour, in this case, you will emit 250 grams of CO2. So everything in the microwave is probably very dead and non-living anymore, but you emitted this amount. If you compare this to a traditional petrol car, if I say it correctly, I am going to switch to an electrical car. I'm still having a Ford Focus. I know for sure for the Ford Focus, this is 2 kilometers in that car. So a very important thing is that why this matters so much lately is that after a longer time, because for the longest time, the hyperscalers, so Microsoft, Google, AWS, they said, well, we have renewables, we have green contracts, we're not emitting any emissions. But now there's all switching, especially in the background, to location-based metrics. That means that where the data center is, they will look, okay, what is the indirect emissions in the grid in the country where they are active? And that is the emissions per kilowatt hour that will happen. So whatever you do in a cloud or at a hyperscaler, you will have indirect emissions. Another maybe thing, if you've never seen it before, if you have just a mobile phone or a tablet or a laptop, most emissions happening while producing it. So let's say certain parts of your laptop are produced in China. It is still part of a lot of organizations, their emissions. So it's not like it's happening there, so it doesn't matter. It is included in the reports, but 80% is while producing the thing and 20% is while running. With modern servers, however, especially with Gen AI, this can be 50-50. So it is not always like, hey, maybe if I run software on a laptop, the emissions is what we there try to measure is less important than while having better improved production of certain device. But it always does matter. But especially with GPUs and with more stronger servers, this is not the same. How do you say it? Divided the same. So one of the things that the Green Software Foundation in 2024 released was a definition on how you can calculate the emissions of software. And I understand if you see this formula for the first time, that is a lot. So I will gonna explain step by step how you can do this. So first, the software carbon intensity, the intensity of carbon emissions by software. The main goal is 0. That would be great. It's going to take a long time before we get there, sadly enough. Yeah, and that device behavior changes sustainable outcomes that I just showed. The core components, and although servers and blades are often built differently than your maybe a desktop computer or a laptop, in many examples, kind of the CPU and the GPU almost always consume the most energy. So that's why I always focus on the CPU in my presentations as from a software engineering perspective. Why? Because we have often a lot of influence on how CPUs behave. Memory is also, of course, important. Memory is a factor lower, depending on a certain setup, maybe 40, 50 watts. If you have SAP HANA, that one is that is a service of SAP that has 200 watt memory blocks. That is a different story, but most of the time the CPU and the GPU consume most energy. Then the disks are often even a factor lower, and then network is even lower. Although there's a lot of numbers about networking on the internet, network is a very difficult resource to calculate the emissions and energy of. Why? Because you share it with someone else. So I always explain this: if you don't take the bus today, do you emit less emissions? And often that is not the case, because the bus is still driving. Unless enough people don't take the bus, then the bus is not driving, and then you don't have those emissions. So network is often wrong calculated and often too high. So let's go to the formula. So I always say, let's say you have the longest request ever. So an HTTP request of 1 hour. So let's say you just click on a button on a website and it goes to the backend. And in this case, this request also triggers the CPU to go 100%. Why? Not because it is what you will see in the field a lot, but it makes this formula a lot easier to understand and to see how it calculates. So in this case, this request is taking an hour. The CPU is, in this case, example is 350 watts. So that means 0.35 kilowatt hour. In this case is another example of the CO2 emissions per kilowatt hour. So in this case, that was 360 grams of CO2 per kilowatt hour. And then we have carbon emissions. In carbon emissions, I could do a complete separate talk about that, because it is everything, all the emissions that, like I said, that happens by, in this case, producing the CPU until it goes to eventually some landfill somewhere, and everything in between, transport. So normally how it works is you divide it by the whole lifetime of the CPU, in this case, that you use it. So for this example, I would just choose 1 gram, because in reality, it often will be probably lower than 1 gram for this example. So how does it then calculate? Well, you take the CPU that was on 100%, so 0.35 kilowatt hour. You multiply that by 360 grams of CO2. You add the 1 gram of CO2 carbon emissions, and then you have, for this one request, you have 127 grams of CO2 emissions. Then a lot of people often say, yeah, but Wilco, if that's just one request, that is not a lot of emissions. Well, a lot of time it is, and I will show it, it is all about scale and how you eventually, if you add everything up, sorry, I will drink something, how it eventually add up together. So this is exactly where I'm now going to. So let's say you were just very, how do you say it, you wanted to try something new today. So you spin up a new container or a virtual machine, probably more a container or a pod, and you forget that you created it. It was for free, was somewhere, and you just leave it on. So the first hour, it only takes 0.18 kilowatt hour. That's not a lot. And then a day, it's 4.32 kilowatt hours, so still not a lot. Then a month, it still keeps running, 24/7, 131 kilowatt hour. Then we go to per year, and then in this case, it's 1,576 kilowatt hour. So digital waste is energy consumption without value often. So in this case, I just leave it running, and yeah, it's still running on some hardware somewhere. So it's really, it's running in the cloud. So let's take this example to 75%. And then we already, so there's a difference in the workload. So I see that this example was a wrong example before, so I will update that in the share of the slide share. This one is 100% correct. I know that for sure. Copy paste error for me, sorry. So in this case, running at 75% utilization with 250 watt system draw, including PUE, 2,365 kilowatt hours per year. Then still, I mean, for some, if you don't have electrical car, that is almost what some households use in electricity. So that's a lot. And that's just one virtual machine or a container. So let's go to 1,000 virtual machines. You already go to 2 million kilowatt hour per year. Then if you start using like the average CO2 emissions in the Netherlands from 2024 at 220 grams of CO2, in the UK it's a bit lower in the same year. You're already going to the 520 metric tons of CO2 per year, which for most sustainability officers in an organization, a lot of organizations have a sustainability officer, it's already a number that it's really getting, it's getting on their radar. If you have a 15,000 virtual machines, you already go to the kilotons. So maybe you're thinking, well, that is such a large number, that will not happen a lot or is non-existent. But think about it. Every system these days, HR, ERP system, everything runs virtual. So if you have a very big organization, let's say with 50,000 people in it, you could get to this number. So the other thing is from the Green Software Foundation is very important that you can invest in biodiversity. Yes, you can offset with certain credits, but the Green Software Foundation really focuses on the point that we try to reduce it instead of offsetting it. So that's why I'm always focusing on the reducing part. So in 2024, the total of all the reports together, there was 41 gigaton of grams of CO2. So that was a lot. Then if you have an example, so in this case, because I always want to put it in perspective, ASML is a company and ASML produces the wafers or the scanners. Without them, you cannot build any AI CPU or GPU. So they're pretty important. They have around 44,000 employees. So this is scope 1, 2, and 3. So maybe a little explainer there. So scope 1 and 2 is the thing you're mainly often responsible for. 2 is often the electricity, like buildings and that kind of stuff. Often if you have your own on-premise IT and that kind of stuff. Scope 1 is like traveling to the office and that kind of stuff. Scope 3 is everything in the chain. From often it is related to suppliers. But external, yeah. So just putting in ballpark numbers, if someone says like green IT or sustainable IT, it doesn't really matter that a lot. If you, this is the 1,000 virtual machine example of 520 metric tons of CO2. But if you have a lot of virtual machines and containers and pods, it really does matter. So, and then even if you think, well, we can just run it to renewables and we're done. Well, just running 100% of renewables doesn't always mean that it's sustainable. And I'm going to try to explain this. So now we finally get to the code for someone who was waiting on that part. So green design versus sustainable design. So what I always try to explain is when I talk about green, I often talk about short term, something you can do today. So you can run in France, although you maybe have some nuclear waste. You can run, of course, in Sweden. It is something you should do it in the long term, but you can already do it in the short term. Sustainable design is often something that you do for the longer period of time. So you design certain software or you code in a certain way so that the software will run in 5 to 10 years and that you don't have to develop everything. I mean, things change, so sometimes you have to recode something, but that not everything changes every 2 years. So often, I get the question, so what is the energy of one line of code or that kind of stuff? I just in a little bit earlier explained that there were these patterns, like you had the utilization. So often we have underutilization, so we don't use the cores enough. We should use them 70-80%. We have waiting patterns and we have bottlenecks. So is there a line of code? This build or this instance create lasting value? That is something you should ask yourself when you code a certain code line or a certain function or a certain program or algorithm. So I'll give you an example. So let's say you really like sorting on data and you think, well, in this case, this is C#, and Microsoft, they can say whatever they want, but I create the quickest sort ever. It is the parallel quick sort in this case. I build it, it's very quick. So how could you measure it? Well, theoretically, because if you would put it in the smallest instruction that the CPU executes, and although hardware, runtime, and operating system has influence on it, so if you're really expert on it, just ignore a little bit and just focus on the theory part of this. In this case, this function operates at 140 to 160 million microoperations. So now we compare it to the .NET sort. Because we know now that running software consumes energy, so if we would make it quicker than the Microsoft sort, we would be doing a better job, right? So then the question is the list sort actually better or worse than the one we created ourselves? Well, in this case, it is almost the same. And in some cases, it was even because the previous one was 140. So therefore, Microsoft, because they also use some runtime tricks, in this case, it is like 120 to 160 million microoperations. By the way, this example is based on a certain amount of a list with a certain amount of items in it and that kind of stuff. It's just the example comparing the one logic with the other. So it's not always that if you build it yourself that it's better. Sometimes it is, but sometimes not. And then someone is like, well, Wilco, this weekend, I'm going one further. I found this really cool library. It is a magic sorter. It has a great a 0-star, and I'm the only one watching this GitHub repository. And it's the best tool ever. Well, what I always say is from a sustainability perspective, the question is, who is going to maintain this in the next 5 to 10 years? So you can always focus on the energy part, but if you create something that creates an issue for supporting and maintaining a certain thing over 5 to 10 years, then maybe that is not the most sustainable thing. So we often think with sustainability, it has a lot of meanings these days and definitions, and it's often very one-on-one with climate, but sustainability has a broader definition and a broader perspective. So yeah, the other thing is, like I said, yeah, making certain things more parallel and async. That can be helpful to utilize the course better. But then the question becomes, because some programming languages are way more efficient than others, I'm going quickly to here also because of time, is like, we're going to build it in Rust. Well, that's amazing, but setting up async coding in Rust is not always the easiest thing to do. So just because maybe a language is has less microoperations when it's executed, doesn't always mean, because you have to train people, and people also need to understand how you can deal with these underutilization, bottlenecks, and waiting patterns. So yeah, I have a great Rust developer in my team, but sadly we can, yeah, it's not easy for everyone to instantly understand Rust and use it. So yeah, Rust async is hard because you must manage who owns what instead of the system doing it for you. And for me, by the way, I'm more like you try to support something in the real world, and you need to be practical sometimes and realistic. And yeah, I think that's also very important. Yeah, so this is what I already said. So yeah, if you don't do it to Rust, are people that maybe gonna avoid async development. So then we get back to the DevOps++. So what is the DevOps++ framework then? Because we talked about all this stuff, but we haven't really talked about the DevOps++. So before we can dive into the DevOps++, we first have to focus a little bit on DevOps itself. So DevOps originally was, of course, set up to break some silos, because we had developers and we had ops people, and kind of they had to work together, but often the developers throw something over the wall, and then the ops people needed to do stuff. So there's a whole process behind it, from planning, coding, building, testing, deploying, running, monitoring, improving, that's going on. So it's very focused often on automatic flow, CI/CD pipelines, infrastructure as code, observability, and main focus was, I think, always faster and safer delivery. So yeah. And then also, because you do that, then hopefully have more feedback loops because of this perspective. So what is then DevOps++, finally? So what we do with DevOps++ is we add a sustainability lens. So the first thing is, and we really believe in this, is you need to detect actions that will lead to reduction of energy use, idle compute, and CO2 footprint. So what you see a lot of happening in our field is that, and I had this for a longer time the same, because you want for the climate to reduce the amount of emissions. So that sometimes you want to know emissions for everything, for code level and that kind of stuff. But to lower it, sometimes you have to understand what the actions are that will eventually lower the amount of energy and emissions. That is an important focus point. And then the other thing that I also kind of talked a little bit about is that if you do it in a sustainable way, hopefully you also extend the lifetime of a device that you're using. So a service is harder, but everyone had this mobile phone that overheated, and that you don't see it directly, but overheating your mobile phone has a negative impact on the device and the battery. So yeah, what we really focus in with DevOps Plus is that that solid code smells, energy efficiency checks are embedded in the CI/CD, but also especially energy focused. So yeah, and also that they only use the energy that you need to deliver certain business value or user impact. So what you can do at some point is, yeah, you can optimize the utilization of a certain function, and then it runs on 70-80% utilization. Well, that's great. But if it's actually not doing something useful, then you optimized it, but it was kind of still a compute waste going on because it didn't actually deliver certain business value or user value. So we eventually came up with 10 core principles from the underutilization, bottlenecks, and waiting pattern. And the first 5 are finding idle and help idle compute to reduce. Then checking out the CPO load versus business value that I just explained. I think the most talked about with organizations that I'm working with is right-sizing memory, because what you often will see with hyperscalers that you choose a certain container or virtual machine, and that the amount of cores, often you have too much cores because you need a certain amount of memory, or the other way around, you have too much memory because you needed a certain amount of cores. Right-sizing, and sometimes that is on purpose from the hyperscalers, sadly enough, but right-sizing memory helps a lot, because if you can run in a smaller container, you also have less energy usage and you have a smaller footprint. Then the fourth one is I/O visibility. So what often happens is that someone thinks, oh, this system is slow. And then the main reason is because there was a delay to the database or to another serverless function or certain things there, or to a disk. So sometimes there are I/O things going on. And if you don't have the I/O visible, you may be just going to upgrade your CPU or memory or such a thing because you think it's slow and I need to make it quicker. Then the fifth one in this one is validate early. So we have ways, and hopefully I have enough time to show this as well, that you can, on pull request level, could in theory test code, especially with observability data together, because sometimes you optimize something and then you run the code and it didn't actually did anything. So code and observability together. So, but do that on pull request level. And we focus for that. We really focus on integration tests. A little bit more about that later. The sixth one is prune data. So if you have a lot of microservices or serverless going on, we often also, I had literally two trainings where literally someone said, well, we started with just a set of JSON and it's like maybe a certain big amount of data, and we move it everywhere. So pruning data to what is actually needed is so important. And not only because of the size, because most of the time it is the compute when you start reading the data, when you translate the data, transform the data, that is the compute where the waste is really going on. Well, the compute location that I already talked about a little bit, lightweight execution. So in the Netherlands, we have a lot of, solar panels on roofs at people's home. And if you would execute something on a WebAssembly or a device instead of the cloud, you can maybe use more of the solar panels. Because if you don't use them, they're literally like eaten by a big resistor. Because we cannot deliver in the Netherlands from the neighborhoods back to the grid. That's kind of an issue here, because the structure was never set up for that. Then the ninth, performance not by perception. So often if something is faster than 2 seconds or 1 second, especially with websites and APIs, you think, it's done, it works. Well, most of the time it could be optimized to like maybe milliseconds, 100 milliseconds. And if you have a million of users, that actually is a big difference in energy consumption. And then the last one is a way where you check the amount of operations per user and make that visible. So how many operations do you need to do something, to deliver something to a screen, or send an email, or do something that eventually ends up at a user? So it's all about the playbook, about detect, expose, fix, and validate. And how do we do that? So we have an AI observability way to detect in code with observability data, detect certain patterns. We use integration tests because integration tests are often used for load testing or for finding issues. But you can use integration testing to find waiting patterns, to find bottlenecks, and to find underutilization. We use the green metric tools from the Green Coding Solutions in Berlin. Afterwards, it can maybe take a few days, but I will also send the links to the things that are open source and that you can use. Then eventually, if you expose, if you know what the issue is, you can fix it. And this can be a code fix, but it can also be an infrastructure as code fix. So let's say I always use the Java example. Let's say in Java, we can make eventually the Java use less memory, then maybe we can use a smaller container to run, as example. And then the last one is you validate. So you use certain tools. You can do this in working together with Ops and also the FinOps people, because they always love it if less stuff runs, that it's cheaper. But you want to validate if your changes actually use less energy, cost less, and emits less emissions. So that is something you do in acceptance and production. So again, how can coding practices reduce energy consumption? So yeah, as an example, I'm hopefully, if I have enough time, I'm gonna do a small demo after a few slides. And today we're part of the Express.js development team. And the Express.js has 5 to 10 billion downloads. You have the GitHub page. It is a quite long-standing, and there's nothing to improve, right? You would expect. I mean, it's open source. A lot of software engineers looked at it, so potentially you would not find that much, you would say. So to explain a little bit what I'm going to show in the Gen AI is that we use a theoretical model that is based on the thing that I explained a little bit in the beginning. So if you're in this theoretical model and you say to Gen AI, like, for each core runs on 1 gigahertz. For it's purely theoretical, but it's for decision making. It makes a lot of sense. 1 hertz is in this case a theoretical model equal to 1 micro operation, and then the 1 gigahertz that runs 1 core at 1.2 volt. That means that with calculation you can have an theoretical estimate of the energy bandwidth of code, and it also then take into account the dynamic voltage and frequent scaling of the CPU cores. So what happens if you give something like this to an AI? So this example is, I'm going to use ChatGPT later. This example is with the GreenPT. It is a ChatGPT alternative running completely on, in this case, Scaleway, the most transparent and hopefully honest, how do you say it, hyperscaler out there, sovereign in Europe. And the GreenPT runs open source models. So yeah, I gave the theoretical model. He very quickly kind of get into the right word cloud, so he knows what we're talking about. Oh, and the cool thing is I then said, like, hey, can you add to each code line, can you add in line the expected amount of micro operations and the expected amount of milliwatt hour? So this is the moment that it starts getting really cool, because then you get even, if you're maybe not familiar with all the functions that you sometimes use or libraries, you get some more insight. Like I said, it's not perfect. It's not that you can use this as exact measurements, but for sustainable decision making, this is, I think, an important thing that you can do. So before I do ChatGPT, I'm always also want to include how much footprint does this cost, because that is, of course, the first question that I always get. So last year, I gave at Kickstart AI, it's a community in the Netherlands, a presentation where I used Olama and I injected Python, not the most green language, but I injected Python into Olama in the model. that I ran on this laptop. I have an NVIDIA 4050, if I'm correct. That's also shown on the dashboard soon. Here we are. Let me pause for a second. So in this dashboard that I created, so on the left side, I have here the open web UI. It looks like ChatGPT, but it's an open source user interface that is on top of Olama. And on the right, I created a static HTML. And what it does, it calls every millisecond it can. It calls the API that I created, a very small Flask API that I created in Python. That runs on the how do you say it, on the Olama environment, and it uses the NVIDIA SDK. So what is different between GPUs and CPUs? With CPUs, we have to do all these difficult stuff to calculate the amount of energy use and cores. With GPUs, especially with NVIDIA, we can just say how much wattage are you now running every few milliseconds, and it is still an estimate, but it's a very accurate one, and will give back the utilization very, very correctly of the system. So if I now run it, I'm going to click start. So the orange line is the utilization. So it's now very low. By the way, if you use like NVIDIA 800s, which are production video or TPUs, they idle on 100 watts. So a graphics card or your gaming machine has a lower idle than hyperscalers. Sadly enough, they do this on purpose because they could do it to 25 watts. What you also see, because I use the 220 grams per kilowatt hour here again, is that we're not that high in the amount of grams, and the amount of energy you see is a lot less higher than maybe a lot of people expect. I validated and compared this with the numbers of Mistral and Google and all that kind of stuff. I also have a podcast where I talk about this episode where I was a guest in. But what you definitely see here, and this is why I'm always saying why Gen AI is way easier to predict than like normal code, is it utilized almost perfectly on 70 or 80%, which means that where with CPUs, you cannot really use time as a proxy. With GPUs and Gen AI, you can. So the amount of time it takes from the moment you start to the moment you have value and you actually getting things back from the model, you can do a very good estimation on how much energy you're using. Although, of course, these days there are way more complex ecosystems behind there, but I want to keep it simple. So this is just a model with inference that we're doing here, and I think it gives a very good insight. So in this case, we ended up now at like 0.36 grams of CO2 emissions. So yeah, then I'm going back to my presentation. Wait. Did I click every? Oh yeah, it's still open here. Yes, so live demo. Let's see if this all works, and if the demo gods are with me today. That's always the question. So I prepped some prompts, and I hope that it's quickly, because with Gen AI, you never know what you're gonna get. So what I did is I went to the, and this, you can do this with your own code as well, right? So this is a cool thing. So when you're done after this session, you can try this out and experiment and debate with me on this on LinkedIn. I would love to get some feedback. But yeah, you can just on the GitHub, you can download the file, you can download the zip. So I already did that. I uploaded to this project. The first thing that I'm going to do is I'm going to extract the file. So what is happening now is that in the Docker instance that we get, or the container instance of OpenAI in this case, you have access to what you upload. So that means if you upload a zip file, you can extract it. You can ask questions about code, which is kind of cool. But we, of course, we're going to look at the green and sustainable perspective of this, because that's why we're here. So yeah, it found 141 JavaScript files. It apparently finds something about it. That it now is talking about microoperations is because I added a system prompt to it. So in the system prompt, there's the theoretical model and certain things from the DevOps playbook that we use. I can share the system prompt afterwards. So yeah, now I know that in this code, because it's always very dangerous also time-wise in a live demo moment to just do random stuff. So I'm going to the application.javascript. And there's always a question if it works. Hopefully it gets with something useful back. I don't know if in the meantime there were questions, by the way. If I didn't already answer them, I'm very sorry. Yeah. So it's doing stuff, we hope. It's working. Most of the time it's doing Python stuff. But it's not doing a lot. Let me see, because of the time I already did a previous one. So I'm gonna quickly, oh wait, that is this one. So I also here, oh wait. I here also extracted the files, and I will wait a bit. So I here experimented here because I was preparing a little bit for getting better prompts for this demo. So I'm looking for the 10 biggest codes. So in this case, the application JS was 14 kilobytes. So I'm looking especially for a file that has some code in it. I will skip a bit. So this is just the application.js, and this is just the code. JavaScript code that is used. That is not like the main focus in this. It is a larger file. So what I then asked is, oh, he's just responded. Add inline comments per code line, how much microoperations and milliwatt hour energy ranges need to execute. And then it adds, like in the example in PowerPoint, it adds examples here. Maybe it doesn't tell you a lot, but maybe a few things. So there are microoperations estimations going on here per code, and the ranges of the potentially energy usage. I'm going to a little bit to the last part. Yes, where I asked, what would you improve based on the milliwatt hour? And it explains a bit that that the router.handle in this case uses the 70 to 90% milliwatt hour, and that you could improve certain things. But what I like more from this example, because what I remember is there were two, and this is what we often do, and this is the clash between energy and between sustainability. For sustainability, you want something readable and reusable. So in this case, the reason that in this framework that they use prototypes is because of this, a certain clean coding style. But this clean coding style is taking from the whole request, whole function, it takes 10 to 15% of the time to execute. So then the question sometimes is the readability of the code, is it worth it compared to something that maybe runs millions of times at a certain point? So I'm not here right now to judge. It's more like an example that you can go look into this with its theoretical model in code. And I don't have enough time to be way more clearer with all the things you can do here. So yeah. So then the last part, how does testing contribute to greener software? So like I said, we really focus on the CI/CD pipeline with DevOps++, so development, test, acceptance, and production. So what we do is we set up integration tests with the Green Metric tool from the Green Software Coding, Green Coding Solutions in Berlin. And we create those tests so that this can be a user journey, this can be a transaction to a database from C# code, C++ code, whatever. You create kind of transactions that you test in a certain integration test to find the waiting patterns, the bottlenecks, and the underutilization. And then you try to improve it. That can lead eventually, if you eventually fix certain things, to hopefully a smaller container or pod. You can have then an infrastructure as code change, and then you can test with acceptance and production if it actually in production uses less energy and emissions. So yeah, you can eventually. So in the beginning, you probably will use still a lot of manual analyzing the code, because a lot of things in this field is immature and still in development, although it's going rapidly. We're really currently focusing on the background with GitHub, using their tools to make this more automated happen. So that's pretty cool. But yeah, the idea is that we can eventually, within a short time frame, do it fully automatically. but only when it makes sense. So if you have a small application that nobody uses, I would not do this. I would mainly focus on things that computes for hours or have a lot of users. Or I always say if it scales a lot, if it has a lot of footprint and it costs a lot, especially with a corporate organization, you can also do it, of course, within a study environment or your own environment to experiment. But from a cost and footprint perspective, it often makes sense only for those cases where the scale is also there. If you want to know more, I write a lot on Medium on my name, Wilke Burgerhoff. There's also a post about these points, fixing friction, 10 examples, principles for DevOps Plus. I will also share that link to my Medium environment. We're building a GitHub page with all the principles that is still in development. But if you have the link, you're very quickly in screenshot, you know where to find it. It is recorded, so it is there. But just note that we're still developing this, and hopefully it gets better and better. And if you want to know more about me and what I do, because I write about this topic every day, I speak about this topic every day, and happily, I'm now in a place where I switch my normal job to completely 100% sustainable job for organizations. So yeah, connect with me and follow me. So that was kind of it.
Amazing. Yeah, that's really interesting. Do you have a couple of minutes for questions? Does anyone want to ask any questions? Feel free to put it in the chat as well, and we can read it out.
I hope that it was not information overload, because I understand that sometimes that is the case. I'm sorry.
Yeah, it's really interesting to see how you're measuring, how you're measuring all of this impact.
Yeah. So is there something in the chat?
Yeah, it's just saying thank you.
Thank you, yes. I don't see any questions. I don't know if...
Yeah.
I'm open for any question. So even if you're like, I'm not sure about this, I really like to help people. So whatever it is about green, sustainable. Oh, thank you. That is great feedback. Awesome.
Yeah, and we will put this on YouTube as well.